The normal types of derivatives that we usually see are derivatives with respect to the coordinates, so x1, x2, and x3, so computing things like the components of the gradients and things like that. What I'd like to do now is discuss briefly what happens if you have a function, whether it be a scalar, vector, or tensor valued function, that is also a function of, say, scalars theta, vectors v, and tensors t. And you'd like to compute the rates of change of your function with respect to these arguments. So the arguments are no longer position, but we can still use the exact same ideas that we use when we take derivatives with respect to position. So for instance, if I want to compute the derivative of f with respect to its scalar argument, the theta, I can apply my directional derivative formula that we use for taking derivatives in general, and I can apply it just in the first argument. So I can replace theta by theta plus alpha h, where h is a scalar. I can take the derivative with respect to alpha, set alpha equal to 0. And what I'm then going to get is I'm going to get the derivative of f with respect to theta times h. And so if I can compute the first part of this expression and then I can isolate away the h, then I can find the derivative of f with respect to theta, its first scalar argument. And we can apply the same types of ideas with respect to the vector argument v and also the tensor argument t. So if I do this with respect to the vector argument, I'm going to replace v with v plus alpha h. I'll take the derivative with respect to alpha, and then I'll set alpha equal to 0. And what that's going to give me is the derivative of f with respect to its vector argument dotted with h. Okay, so if I can compute the left-hand side here and I can isolate out the h, then I can find the derivative of f with respect to v. And written out initially, this is the derivative of f with respect to vi, hi. So there's a dot product there between the v and the h. And we can keep going. We can also do this with the tensor argument. So I can replace t with t plus alpha h, where now my h here is a tensor. Up here in the vector case it was a vector, and in the scalar case it was a scalar. So I keep changing what it is. But I take now the derivative of this expression here with respect to alpha, set alpha equal to 0. And what that's going to give me is the derivative of f with respect to the tensor double contracted with h. So if I can isolate out the h, then I'll be able to determine what the derivative of f is with respect to t. And if I write this in components, that's the derivative of f with respect to tij times hij. So these are sort of generalized expressions here for taking derivatives, and they just build off the directional derivative formula that we're used to for positional derivatives. So let's go ahead and have a look at an example here. And I'm going to have a scalar valued function f as a function of a tensor t, and the function is going to just be the norm of t. So and that's just simply defined as the square root of t double contracted with t. And let's go ahead and see if we can compute the derivative of f with respect to t. So that's my goal. So what I'm going to do is I'm going to apply my general directional derivative formula using in the slot t. There's only one slot here. So I'll write the square root of t plus alpha h double contracted with t plus alpha h, evaluated at alpha equals 0. So again, I'm going to have to use the chain rule of differentiation and then the product rule of differentiation. So if I use the chain rule, I'm going to get 1/2 1 over the square root of all of this stuff here. So I won't write it out because it's a big mess. And then I take the derivative of the argument of the square root with respect to alpha. So then alpha appears in two spots. So in the first spot, when I take the derivative with respect to alpha, I'll get an h. And the t plus alpha h goes along for the ride. And then I take the derivative with respect to the second alpha, and that's going to give me an h here. And then the first t plus alpha h goes along for the ride, and then I have to set alpha equals to 0. So if I set alpha equals to 0, I'll have the 1/2. That just follows. This square root here is just going to be the norm of t. And then in the square brackets here, I'm just going to have t double contracted with h plus h double contracted with t. And those are both the exact same thing, so I can collapse them together. And I'm going to end up with t divided by the norm of t double contracted with h. So you can see I've already isolated out the h with a double contraction, and so what I have in front of the double contraction of h is the norm, or sorry, it's the tensor t divided by the norm of t, and identify that as the derivative of f with respect to t. So this is a way in which you can calculate the derivatives of arbitrary types of functions with respect to arbitrary arguments. If I want to write this additionally, I'll have that the components will be the derivative of f with respect to tij is equal to tij divided by the square root of tkl. Okay, so down here, that's my norm of t, and up here I have the components of t. So just written in a different way.